putting you on the spotlight now. So we've got, I'll let them introduce themselves, but we do have those three speakers. Take it away, Paolo.
Okay, I'm Paulo Mota. So we are in an interesting moment in the history of repair because now we are going to fix repair. No, actually we are making repair automatic is like a big dream of Cassandra, right? So we are now having two efforts to make this happen. One is to take normal repairs and schedule them automatically, and another one is take a totally different approach, which is a mutation-based repair, which runs continuously on the background. So the idea here is to present a little bit of this. So Marcus Olsen from Ericsson will present the scheduled repairs approach, and Marcus Ericsson will present the mutation-based repair. And I will just present the problem space here. And the idea here is more to gather feedback, because we all know repair is a big pain point. So tomorrow at the discussion, if you have any suggestions for how we can make this work, and we can also rethink repair. That's a good chance to rethink repair and see what went wrong and what we can improve with this effort. So yeah, I mean, for the last 5 years, we want to make repair automated. So this was probably the first ticket that wanted to make this. And the last milestone was make a repair incremental. So now it's not proportional to the whole data size, but only to the ingested data. So this means we can make this more continuous, and it means we also need to run repair more often. So why we should have built-in automated repairs? First reason is operational simplicity, right? We don't want to have an external service and manage that to run repairs, and we don't want to build repair schedules manually. And besides that, with continuous repair, we can amortize the impact of repair, which right now is very bulky, and have like a more continuous approach, which will improve predictability and also capacity planning, because if repair is always running, you can know when repairs are falling behind and stuff like this. Having built-in repairs will allow us to have more opportunities for self-tuning and optimization. We can know exactly when a table needs repairing and prioritize that. That's a bit harder when you have an external service management. And GC gray seconds, people don't understand it, we can get rid of it if we ensure that repair is being running continuously. Also, right now with anti-compaction, we have a compaction strategy for unrepaired data and repaired data. This means that if you take too long to run repair, you will increase the write amplification. But if we can ensure we achieve an objective of repairing data constantly, then we can optimize that a bit and just keep unrepaired data on L0 for LCS. So, I mean, the vision that we have is to have, I don't know, 1 year from now, repair as a table property. So you can just set, okay, I will have an objective, okay, keep the unrepaired threshold at 10%, and then Cassandra automatically repairs that. Or you can have different repair strategies, like, okay, for specific data set, mutation-based repair is better. So this is pretty open right now. We're just starting with this. So if you have any ideas, just come by tomorrow to the discussion. And the idea is to synchronize this effort, so we have like a consistent syntax and stuff like this, so we don't take different approaches and they're totally different. Like maybe we can start thinking about repair strategies. We have like a common executor. Right now you can execute many repairs and that you just trash your cluster. So maybe we can have one executor and make sure that we keep utilization thresholds at a certain level. Like you can, right now for throttling you need to do compaction throttling and stream throttling. Maybe we can have one repair throttling metric and use that for all types of repairs. Incremental repairs. How to automate them. do you make them staggered as they are now, or is it possible to all the cluster constantly being repaired? Metrics and instrumentation. Since we are taking two different approaches for repair, maybe we can compare them with similar metrics. So amount of data pending repair, the mismatch percentage, and the transfer bias, if there is overstreaming going on or not. So we can also, tomorrow you can suggest metrics to improve repair. And I mean, we are all open to new repair improvements, like how to reduce overstreaming. There are some tickets open that maybe cache digests with SS tables, so we don't do repeated work. Anti-compaction is pretty intensive, so how can we improve that and make that less intensive? So this is all open questions that we can discuss. Now, Marcos also will present his work on automatic repair scheduling, which is one of the alternatives for automating repairs in Cassandra.
Thanks. Yeah. Hi, my name is Marcos Olsen, and I'm currently working on this automatic repair scheduling, which is about decentralizing or creating a decentralized repair scheduling mechanism inside of Cassandra. So why should we do this now? Well, we have all the ingredients, so we have the repair history, and based on that, we should be able to create some kind of comparable priority across the cluster. We also have comparable set in TTL. The repair history and comparable priority will basically be used for the actual scheduling, while the comparison in TTL should be used for coordinating which node does the work.
Sorry, what do you mean by comparable priority?
Kind of a comparable priority between the repair of the table. So which table has the highest priority for repair right now? Based on the repair history, we should be able to deduce that. And then also that each node keeps itself the same. So each node will make sure that, okay, my data is compared to the other nodes. And then how would we do this? Well, if we start off with some repair history, for a certain node, we might know that, okay, the ingredients table here has been prepared at 5 a.m. and the recipes has been prepared at 6 a.m. This means that the ingredients should have a higher priority in the local queue of the node. If we then take this into a distributed view, each node will have their own local queues with their priorities based on what they think is the most important. So based on this, then we can create distributed priority lists, where in this case we have node A and C, which both has a priority of 5, while node B and D has slightly lower priority. And this means that node A and C will be the nodes that are able to perform a repair right now. Perhaps this is where we introduce a distributed resource lease table, which we use compare and set to make node A and C decide between them which node should do the repair. And in this case, node A got the lease, so it's allowable to repair right now. And that's basically the scheduling part of it. So how would we get this going, like for a user? So a user will basically just do some table level configurations where we say that, okay, I want this table to be repaired each 24 hours. I want it to be incremental and per B node. And that should be it, more or less. So some open discussion points that I think could be interesting, I'm sure there are more, are like failure handling. But what if we have unavailable nodes? How should we handle that scenario? Should we kind of postpone repairs? Should we kind of force them in the replicas that are available? Or we also have some other maintenance work like cleanup. Could that also be automatically scheduled between nodes? And we also have other local maintenance work like compaction. Could that also be scheduled? That we schedule based on which table has the highest priority for compaction right now. There's also some challenges with dividing the repair sessions, because if we divide the repair work too much, we might get too much overhead from anti-compaction if we have incremental repairs. We also have multiple data center scenarios which we need to handle. It might be that we have a full data center that is unbig, where we might also allow parallel repairs in the case that two nodes are liable to run repairs at the same time. But we might not want both of these to stream across data centers, because that might be too much load. And also a bit of scope for the ticket itself. If we assume that this is a good solution, what are the features that we require, that we need to have before we can actually go further with and perhaps get this into the code base before we improve it further? Thank you. And now on to Marcus Eriksson with mutation-based repairs.
Thank you.
Sorry.
Yeah, it's good. Okay, so this is a totally different approach to repair that I've been working on a bit. Most of the things I'm going to talk about are up in the air for how we're actually going to solve them. But anyway, so repair obviously has a few problems. Wide partitions. If you have one cell mismatch, you're going to stream the whole partition at least, depending on your market trees. With vNodes, you get the SS-table explosions of the repair. Incremental repair helps a bit. vNodes will still be painful. You're still going to get many SS-tables. They might be smaller and not as many, but still very many. And sometimes you still need to do a full repair. And if you've only been running incremental repairs for a year, you have no idea how long time a full repair is going to take. And as we mentioned, coordination is painful and complex. Croniops or repair services. So the basic idea of mutation-based repair is that each node pages through its local data and does reads from other nodes to make sure that the data is in sync. An example, the yellow boxes are the partition keys, or primary keys. And now we have the SQL rows lined up like this. Very simplified for this works. So we start by reading up a page of data. In this example, we have a page size of 3. And we hash the data in that page, and we figure out which the first and the last primary keys we actually read were. And we have replicas. The replica reads out the data in the same window, hashes the data, and compares the hash it got from node 1. So, and we limit the amount of rows read up to 2 times the page size. And I'll get back to why we do it. So in this case, we get a mismatch, and node 2 is going to reply with the actual data it had in the window. And then when node 1 gets that data, it's going to take a diff between the data it already has and the data it got from node 2, and only write the actual cells that mismatch.
So how does this compare to repair?
It's very similar to repair. It uses the same code.
Okay.
And then we continue with the next page. So overview, if the hashes matches, we just reply with a match message and we continue with the next page. Just a small mismatch, we do what I showed. But there's a few corner cases. So if you lose data on one node, for example, the amount of data on the remote node is going to be very big. So we need to special handle that. In this case, it's going to reply, okay, I have a lot of data in that window, and the repairing node is going to start paging back the data. And in this case, we don't do any diffing between the local and the remote data. Instead, we just write it to disk. And the reasoning there is that if we just have very few local rows and very many remote rows, the diffing is not going to help you much. And we save the last repair range in a system table. So if a node dies and we restart it, we can start repairing from exactly where it left off. It's currently implemented as a node command, but I hope this could be a continuous process that always runs, always slowly paging through the data on the local. So the benefits over the current repair we have, you won't have any problems with wide partitions. We page up SQL rows. We don't care about V nodes. Every mutation goes into a mem table, and that mem table is flashed periodically, just like any other write. We won't overstream, since we do the diffing between the local and the remote data. We won't need any coordination. Every node always repairs itself. And by always, I mean always, so it should always be running. And instead of this big overhead when you trigger a node to repair today, we're going to have a small overhead that's pretty constant over time, hopefully. So the way I describe it is that each node reads data from other nodes to make sure that it is up to date. It might be a better idea to have one node guarantee that its replicas have the same data as I do, because then if I know that I've been sending all my tombstones to replicas, then I can drop my local tombstone, right? So it might make more sense to reverse how it works. Yeah, maybe we should make it incremental. We probably need it, but anti-compaction is very painful, and it would be nice if we could figure out a way to make it incremental and not have to do anti-compaction. Yeah, put stuff in a separate mem table. That way we can skip commit log, and instead, whenever we flush the repair data, we can just mark that range as repaired. So if we lose the data in that repair mem table, we just start over from when we last flushed the mem table. Yeah, and we need to figure out how to make it a continuous process, how we rate limit, how we set pitches, stuff like that. It would be nice if we could make this totally invisible to the operator. It's just something that carries on. And currently, can we have easy gray seconds in a way, better way we do this? If I know that I have sent all my tombstones and data to my replicas, we can probably drop the tombstones. Yeah, and currently it breaks data compaction and timing, because it brings in old mutations in a new mem table. And that's not very good. Okay.
Sorry, can we go back to the previous slide?
Questions?
All right, as long as you post these slides somewhere.
Yeah.
Thanks, guys.